Hey guys, and welcome back to another video on the channel. In today's video we're going to be looking at proof by induction, or pretty much an introduction to it. So proof by induction is pretty much the only proofing technique you really do in the Queensland syllabus for year 12. So let's pretty much get straight into it. So proof by induction pretty much means you have some formula or something where you have n or whatever letter they're using, and you pretty much go prove the left hand side equals the right hand side. So the way you do it is pretty much a step-by-step process. So step 1, you prove it's true for n equals 1, then you assume it's true and let n equal k, and then you show it's true for k plus 1. So what they have is let p of n be some preposition about the natural number n. We can prove that p of n is true for every natural number as follows. So step 1, prove that n equals 1 is true, and then show that every number k, p of k is true, and then the number after k, which is k plus 1. So it's a bit of a weird step how they've written it here. It's much better to see it just in action straight away. So we're going to get straight into a basic example of proof by induction. So this is probably a basic question you would get with proof by induction. This could actually be a year 11 question as well as a year 12 one, but it's just good to start off with the basic one. Now what we've got to do is we've got to prove that this is the same as this. Now let's actually unpack what this is actually saying. The sum from 1 plus 3 plus 5, so pretty much all the odd numbers up until some odd number, is equal to that odd number squared. So what it's saying is, alright, this does not equal this on its own. This is only true for n equals 1. So what I mean by that is, alright, when n equals 1, we plug it into here and we get 2 of 1 minus 1, and we get, well, 1. We plug that into this side and we also get, so this is our left hand side. So we have 2n minus 1, and then we have n squared, which is our right hand side. So n equals 1, and you sub it into here as well, and you get 1. Now if I go n equals 2, you need to include this term as well for the left hand side, because it's the sum. This sum is equivalent to this. Because if I plug in n equals 2 into this formula again, 2 of 2 minus 1, I'm going to get 3, and here I'm going to get 4. And you probably notice, oh, 3 doesn't equal 4. However, this added with that equals that. So that's why this infinite sum is equal to this. And if I kept going, I'd go, alright, when n equals 3, I would get 2 times by 3 minus 1, which is going to give me 5. So 1 plus 3 plus 5 is going to be the same as 3 squared, which is 9. So notice how the sum is equivalent to this here, pretty much, all the time. So all this is equal, and all of that is equal. So it's the sum that's including it. So now that we understand what we're actually trying to prove, and what is actually going on here, because at the start, before you even start proving, you've got to understand what this pretty much equation is saying. So this entire side is equivalent to this entire side for some number, pretty much, n. So they've said n is a natural number, and pretty much we start off with, alright, step 1, let n equal 1. So left hand side, we just write this, which would be 2 times 1 minus 1. So you get 1. Right hand side, we get 1 squared, which is 1. And then you go, alright, 1 equals 1. Left hand side equals right hand side. Hence, true for n equals 1. Okay? So that's step 1 of proof by induction. Step 2 is assuming that it's true now. Now, when you assume that it's true, because the reason why we have to assume it's true is because we can't go through every single number, because that's an infinite set. So what we do pretty much is, alright, assume true, and let n equal k. But k needs to be some number in this same set here. So k needs to belong to whatever set they've defined, so natural numbers again. Okay. So what we do now is rewrite this entire formula in terms of k. So 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 equals k squared. Okay. Then you're going to assume it's true for the number after k, and the number after k is k plus 1. So assume true for k plus 1. And you don't need to define that because you've already defined k previously. So now what we do is, alright, we've got to write this bit. So this is the sum term. You need to include the term after this as well. So this is k, and you're going to have to include k plus 1 here as well. So what we do is we rewrite the whole thing and go, alright, 1 plus 3 plus 5 plus ... plus 2k minus 1. That would be only up to k, but you've got to include for k plus 1. So you have to add the next term, which is k plus 1. So that's the sum side, and then on the right hand side you just replace k with k plus 1. The only extra term you need to add was this, is because this is a sum. So this is for k equals 1, k equals 2, k, and then k plus 1, etc. pretty much. So once you've done that, you have to pretty much make note that this is exactly the same as this. So what we can do is substitute this entire infinite thing for just k squared. So if we do that, this is called the inductive step. So once you put that in, you get k squared, and this is what you get. And now, what we have to do is prove the left-hand side equals the right-hand side. So now I'm going to get rid of this. Mind you, you would keep all of this working when writing this stuff out. So let's get rid of that and that. And what we're going to do is show the left-hand side equals the right-hand side. Now you can't cross out stuff on each side, because then you would get 0 equals 0, which is kind of cheating. So what we're going to do is slowly expand this. So we're going to get k squared plus, distribute this, 2k plus 2 minus 1. And then let's expand this. So this will be k plus 1 times by k plus 1. So multiply this by that, and that, that, and that. On this side here, you're going to get k squared plus 2k plus 1. And over here, you're going to get k squared plus 2k plus 1. So we've proved the left-hand side equals the right-hand side. Hence, we've approved this equation here. Because we've proved it, alright, it's true for n equals 1, n equals k, where k can be any number in that set, and the number afterwards, so n equals k plus 1. So we've proved all three, pretty much. So that's pretty much it, proof by induction. Little basic example, but it's the exact same steps for every single one in Specialist. Alright? So let's move on to the next example, and let's do the exact same thing. Now the next example is a bit different because it's not proving left-hand side equals right-hand side, it's proving divisibility pretty much. So let's just take a look at it. So example 25 that I've chosen is prove by induction that 7 to the power of n minus 4 is divisible by 3 for n belongs to the natural numbers. Okay, so what pretty much this means is no matter what number I put in for n, I can divide it by 3 pretty much. That's what it says when it means divisible. So we go step 1, n equals 1. So then you're going to have 7 to the power of 1 minus 4, and that's going to give us 3. 3 divided by 3 is 1, so therefore it's true for n equals 1. Step 2 is you're going to assume it's true and let n equal k. And then you have to define the set that k is in, so k belongs to the natural numbers. And what I'm going to do now is actually introduce another letter. So since it's divisible by 3, 7 to the power of k minus 4 is equal to 3 times some number a. So I'm also going to introduce another number, a, where a is also a natural number. Okay. So once we've done that bit, what we're going to do is the exact same bit and prove pretty much for k plus 1. So now I'm going to get rid of this stuff here because we don't need it anymore. But keep that working in like your book, obviously, and if you're like doing a test as well. I'm just rubbing it out because I'm going to need room. Right, so assume true for k plus 1, and then I'm going to define another letter b. So b belongs to natural numbers, and you'll see why in a sec. Because I'm going to have 7 k plus 1 minus 4 is equal to a multiple of 3 times some number b. Because this is divisible by 3, so 3 times some number b is this. Now it can't be the same as a because they could be slightly different, and they probably are slightly different. So what we're going to do now is somehow put this equation here into here. So what I'm going to do is, alright, let's take a look at 7 to the power of k plus 1. If I break that up using index laws, isn't it the same as 7 times to the power of 7k? I could rearrange equation 1 to make 7k the subject, because if I moved this 4 to the other side, I would get 7k equals 3a plus 4. So let's just do that real quick. So if I move that there, I would have 7k equals 3a plus 4. So now I've got an expression for 7k. So what I'm going to do is, alright, I'm going to change how that looks really quick. I'm going to apply my index law here, so I'll have 7 times by 7 to the power of k minus 4 equals 3b. Then I'm going to substitute this in for 7k because it's equal to it. So what I'm going to get is 7 times by 3a plus 4 minus 4 equals 3b. I'm going to distribute my 7, and I'll get 21a plus 28 minus 4 equals 3b. So I'll get 21a plus 24 equals 3b. And I can see both of them, I can take out a factor of 3. So 21 divided by 3 is 7, and 24 divided by 3 is 8. So I can rewrite that as 7a plus 8 equals 3b. And I've proved that this side is divisible by 3 because I could take out a factor of 3. So therefore I can say, hence divisible by 3. And that's it pretty much. So those are pretty much your standard proof by inductions. Now these are basic ones, the ones that I've covered here. They can get a lot more complex other than this, and they can actually include trigonometry as well. But let's take a look at another example for this part, and then I'll probably do a second part for this video. So, prove the following, well, each of the following, so I've taken this from the book, so just prove the following by mathematical induction, so that this side equals this side. So, step 1, n equals 1. So, left hand side is just going to be 1 because that's all we would have. This side, right hand side, we'd have 1 times by 1 plus 1 all over 2, which gives me 2 divided by 2, which is 1. So therefore left hand side equals right hand side, hence true for n equals 1. And that's it for the first bit. Alright, I'm going to rub this out because we've got to do the next step, and we don't have enough room for that on this PowerPoint. So, step 2, assume true. Oh, I forgot that. Assume true. Let n equal k, and let's just say n was an integer. That's a terrible looking z, so I'll just use a z like that. So k is defined as an integer. So what we're going to have is 1 plus 2 plus dot 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 plus k equals k times by k plus 1 all on 2. Then you're going to assume true for k plus 1. So now we rewrite that as 1 plus 2 plus dot 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 plus k plus k plus 1 equals, and then you're going to have k plus 1 times by, well, k plus 1 all on 2. So I've just substituted wherever there was a k, I put that k plus 1 there. And I put the k plus 1 here because this is a summation, so you have to include the next term. Okay. So hopefully you can identify that. Okay, let's get rid of that. You can identify that this is the same as that. So what I can do is substitute this into there. So what we're going to have is, alright, k times k plus 1 on 2 plus k plus 1 equals k plus 1 multiplied by k plus 2 all on 2. Okay, I'm going to rub this out now because I need room for the algebra. Right, so I'm just going to select that. So now we've got to prove the left hand side equals the right hand side. So do not cross cancel anything at the moment. What want you to pretty much change how the left hand side looks. So if we do that, what we can do is, if I move that to the side, I can times this term by 1, so 2 over 2. So what we're going to have is k on k plus 1 on 2 plus 2 on k plus 1 all on 2. They have common denominators, so you can add the 2 together. So put it all over one fraction. And that's what we have there. Equals this. Now I'm going to multiply this stuff out. And you're going to get k squared plus k plus 2k plus 2 all on 2. Here you're going to get k squared, k, 2k, and then 2. So what we're going to have is k squared plus k plus 2k plus, that's a plus in there, not a multiplication, plus 2 all on 2 is equivalent to this. So if I replace that with its side, we can see the left hand side equals the right hand side. So left hand side equals right hand side, hence true. Ta-da! That's it. Righto, so I'll do a part 2 where I take a look at these examples here, and then that will be it for this video.